Welcome to the Deep Dive. Today, we are taking a really fascinating look at the body's internal plumbing system. We're talking about how it creates and manages blood vessels, a process known as angiogenesis. And if you've ever, watched a cut heal or wondered how a tumor gets its blood supply, you've seen this in action. It's just foundational to life, but also to disease.
That's a perfect way to frame it. We're diving into a pretty complex stack of technical and clinical sources today. Our mission is really to unpack this dual nature of angiogenesis. So how it's essential for health, for recovery, but at the same time, how it can act as the fuel that lets a disease become truly malignant.
Okay, so let's get right into it. We should probably start with definitions because the sources are very clear that there isn't just one way the body builds blood vessels.
Right. You have to distinguish between, let's say, building from scratch and just expanding what's already there. So first you have vasculogenesis.
Vasculogenesis.
This is the de novo creation, the initial primitive build. It's where these endothelial precursor cells, or angioblasts, they differentiate and assemble the very first network.
So that's embryonic then, building the initial highway system for a fetus?
Primarily, yes. It's the original blueprint. Now, angiogenesis is the other side of that coin. It's the continuous expansion and maintenance. It's the process of forming brand new vessels, specifically these little capillaries, from vessels that already exist.
And that's what's happening throughout our lives, right? For growth and wound healing.
Exactly. And if angiogenesis is the expansion, the sources show us there are a couple different ways it can happen. The most well-known is sprouting angiogenesis. This is where a blood vessel literally sends out a new bud like a branch on a tree. But there's also a quieter method called intussusception.
Intussusception?
Yeah, non-sprouting. The vessel basically splits internally. It remodels and divides one channel into two without all the drama of sprouting new tissue.
Let's zoom in on that sprouting, though, because that seems to be the main event. How does the body or a tumor tell a vessel to start that process? The sources lay out this six-step signal chain.
It's this magnificent coordination, really, and it all begins with a distress call.
Okay, step one, the signal.
The signal is hypoxia,
Lack of oxygen.
a lack of oxygen in the surrounding tissue. If tissue is damaged or a tumor is growing too fast, the cells start to starve. And this hypoxic environment, it stabilizes a critical molecule called HIF1. Think of HIF1 as the foreman who gets the alert and then starts shouting orders to release growth factors.
And among all those factors, there's one that's king.
That's vascular endothelial growth factor, VEGF. The sources just keep coming back to it. It's the single most important factor, the master key that unlocks the whole construction site.
Okay, so the order's been received. Step two must be clearing the site, right? You can't build if something's in the way.
Exactly. The existing vessel is wrapped in something called the basement membrane, and it's guarded by cells called pericytes. That same hypoxia signal triggers what's called proteolytic degradation.
So enzymes that destroy things.
Right. Molecules like MMPs, they act like biological bulldozers. They break down the membrane and force those protective parasites to just detach. The site is now open for business.
The site is cleared, so now for step three, exploration. You need a scout.
This is the role of the specialized tip cells. Think of them as pioneers. They don't multiply, they don't proliferate, but they are highly migratory. They sense the VEGF gradient and just follow it like a beacon using receptors like VEGFR2. They're mapping the new route.
And once the pioneer has the route, step four must be the actual construction crew.
That's where the stalk cells come in. Right behind that tip cell, other endothelial cells differentiate into these highly proliferative stalk cells. They form the main body, the tube of the new vessel, basically chasing that migrating scout cell.
Now, this can't just be allowed to run wild, can it? So step five is regulation, some kind of quality control.
It absolutely is. I mean, if all the cells were just tip cells, you'd have chaos, just uncontrolled branching. This is where the DLL4 notch pathway comes in. When VEGF stimulates the sprout, it also triggers DLL4, which binds to notch receptors on the cells next to it. And that signal essentially tells them, okay, stop migrating, just form a stable tube.
So it's the governor on the engine, prevents hypersprouting.
Precisely. And that leads to the final step, step 6. The new pipe is fragile, it's leaky, needs to be reinforced. Stabilization.
Okay.
This is where a molecule called PDGFB comes in. It stimulates the re-recruitment of those parasites we mentioned, the protective cells. They come back and wrap around the new vessel wall.
So the parasites are like the rebar and concrete. They make the new pipe strong so it doesn't leak.
That's a great analogy. That attachment stabilizes everything. And importantly, it also makes the new vessel less responsive to future VEGF signals. The job is done.
But what happens when that incredible six-step plan gets hijacked? And that, I think, brings us to the crucial idea of the angiogenic switch.
The switch is everything.
Mm.
It's the tipping point between health and disease. Angiogenesis is normally kept quiet by this delicate balance between pro-angiogenic factors, the activators like VEGF, and the endogenous inhibitors,
Big breaks.
the brakes, things like angiostatin and endostatin.
So in a healthy state, the gas and the brakes are in perfect harmony.
That's right. But when a disease, like a dormant tumor, flips that switch, it just floods the zone with activators. It overwhelms the natural brakes. And that's the moment a benign cluster of cells can become a metastatic threat.
It's still incredible that Dr. Judith Folkman proposed this all the way back in 1971. The idea that cancer needs infrastructure, not just runaway cell division, must have been revolutionary.
It changed everything. His insight was that cancer cells can't survive without a pipeline for oxygen and nutrients. So they aggressively release these growth signals to force healthy vessels to sprout into the tumor.
They build their own supply chain.
And they are incredibly clever about it. The sources show they use multiple tactics, not just sprouting. They can use vasculogenesis, pulling in progenitor cells from the bone marrow, or they can use co-option, where they just grow along existing vessels, sort of hijacking the existing infrastructure.
Wait, and then there's vascular mimicry. I mean, are you saying the cancer cells literally become their own plumbing?
That is the critical concern, yes. With vascular mimicry, some aggressive tumor cells can differentiate and form vessel-like channels themselves, completely bypassing the need for true endothelial cells.
So a drug that targets the endothelial cells or the VEGF signal might be useless against that tactic.
It might be, yes. It creates resistance. It forces a change in therapeutic strategy.
And this switch isn't just for cancer. It's active in other chronic diseases, too.
Absolutely. Think about diabetes, especially in the eye. Long-term complications cause hypoxia and a massive excess of VEGF in the retina. This drives what's called proliferative diabetic retinopathy, PDR. You get these new leaky vessels that cause bleeding and vision loss. And the sources point out that high blood sugar makes it worse, increasing inflammation and permeability.
So it's clear that managing this whole process is key to health. So given that, the obvious next step is, how do we shut it down?
The goal is always disruption. And the drug designs primarily target the endothelial cells in two ways, directly or indirectly.
Okay, let's start with the direct approach, hitting the construction crew itself.
The most famous example here is bevacizumab, or Avastin. It's a monoclonal antibody. And its strategy is simple. It acts like a sponge. It just binds up and sequesters all the active VEGF, so the signal never even reaches the receptors on the cells.
It cuts the communication line.
Completely. It's a critical therapy for things like metastatic colorectal cancer.
What about those natural inhibitors you mentioned? Can we use them?
We are. Endostatin, for example.
Hmm.
It's a natural anti-angiogenic protein that directly inhibits endothelial cell proliferation. And a key finding is that it does not seem to affect normal wound healing, which is a huge clinical advantage.
Okay, so that's the direct attack. What about the indirect one? Blocking the production of the signal in the first place.
Indirect inhibitors target the tumor cells themselves upstream. They block their ability to even synthesize these pro-angiogenic proteins. So a drug like Iressa or gefitinib is a tyrosine kinase inhibitor, a TKI. It blocks the epidermal growth factor receptor, which is an important signaling hub in the cancer cell. Block that, and you block the eventual release of VEGF.
The TKIs are a massive class of drugs now, right?
Huge. The sources list 7 approved anti-angiogenic TKIs, plus we have mTOR inhibitors. There are many ways to interrupt the process.
But the disease always tries to outsmart the medicine. The sources must talk about resistance to these therapies.
They do. This is the biggest clinical hurdle. Tumors are just incredibly resilient. They develop resistance in 4 main ways.
You learn to adapt.
They do. First, they can just amplify production, flood the system with so much VEGF that the drug is overwhelmed. Second, they can pivot. They start secreting a whole panel of different growth factors like FGF or ephrins, making a VEGF-specific blocker useless.
So they diversify their portfolio.
Exactly. Third, they can recruit help from the bone marrow using vasculogenesis. And fourth, they fall back on those other tactics we discussed. Vessel co-option or vascular mimicry. If you block the main highway, they just use the back roads.
That was a tremendous look at life's essential plumbing. We went from the basic difference between vasculogenesis and angiogenesis through that incredibly complex 6-step signal chain, and we saw how molecules like VEGF are the ultimate gatekeepers for everything from healing a cut to feeding a lethal tumor.
And I think the key takeaway for you is grasping that clinical challenge. Modern medicine has to figure out how to control a mechanism that is absolutely vital for your daily survival,
Well,
while simultaneously being able to shut it down with precision, stop a disease. It's a real tightrope walk.
and on that note, we'll leave you with a provocative thought that came out of these sources. We mentioned that endostatin, a direct inhibitor, is considered safe because it doesn't mess with essential wound healing. This suggests there's a subtle but critical difference between how healthy and pathological angiogenesis works. So this raises a question for the future. If we can modulate this switch with such precision, could we eventually engineer treatments that not only stop tumors, but could actually encourage beneficial, healthy vessel growth in tissues that need it, like in heart disease, without that risk of activating disease? That's something to ponder until the next deep dive.